yourself muted unless you have some urgent questions. Peter, the screen is yours, please.
Perfect. Thanks very much for that very nice introduction, Ewa. So the title of my talk is A Sample Path Large Deviation Principle for Dynamic Erdős-Rényi Random Graphs. And this is joint work with Frank den Hollander and Michel Manges. So I'd like to tell you about my research on dynamic Erdős-Rényi random graphs, but this is also an opportunity for me to introduce a couple of concepts that you may not be familiar with. So in particular, I want to talk about sample path large deviations. And I also want to introduce the space of graphons, which has led to a lot of innovations in the field of graph theory in the past 10 years. So really three things: sample path large deviations, graphons, and then my research at the end, which involves these things. Okay, so let's start with some motivation. And let's just recall the definition of the Erdős-Rényi random graph. Okay, so we're going to say that it has n vertices. Okay, so n vertices. So in this particular example, there's 1, 2, 3, 4, 5 vertices, so n is 5. And each edge is on with probability p independently of the other edges. Okay, so this is an edge here that's off, and that occurs with probability 1 minus p. And this here is an edge that's on, that occurs with probability p. And we're going to be, in this talk, we're going to be primarily interested in questions about the subgraph density. Okay, so this is going to denote the triangle density. So in this particular outcome of our graph, we have just one single triangle. Okay. So there's one triangle, but if it was a complete graph, then there would be 5 choose 3 triangles. Okay, so the subgraph density here is 1, which is the number of triangles, divided by 10, which is the total number of triangles there would be if every edge was present. Okay. The expected triangle density is p cubed, and that's due to the fact that for a triangle to actually to be an actual triangle, so for a potential triangle to be an actual triangle, so here is a potential triangle, then every edge has to be on, and that occurs with probability p cubed because all the edges are independent. Okay, so we know what the expected value of the edge density is. And we also have a law of large numbers for the edge density. Okay, so we know that as the number of vertices goes to infinity, the edge density converges in probability to its expected value. Okay. But this talk is going to concern large deviations, so rare events. So how we're going to ask questions like, how unlikely is the event that the triangle density is unusually large? Okay, so we know due to this law of large numbers that this event, the probability of this event is going to vanish to 0 as n goes to infinity. Okay, but we want to know how quickly it goes to 0. Okay, so that's an example of a large deviation. And we also want to know if we can say anything about the structure of the graph given this event occurs. Okay, so suppose this event does occur and we have an unusually large triangle density, then we're going to require a whole bunch of additional edges. So are these edges kind of sprinkled uniformly around the graph, in which case our graph would look like an Erdős-Rényi random graph with a higher edge probability? Or are these edges arranged in some kind of special structure? Okay, in which case the graph wouldn't look like an Erdős-Rényi random graph. So these had been open questions for quite a long period of time, but they were finally answered by Chatterjee and Variational in 2011. And they used a large deviation principle for Erdős-Rényi random graphs to answer these questions. Okay. So in this talk, we're going to be considering the dynamic equivalent. Okay, so we're going to consider dynamic Erdős-Rényi random graphs. Okay, so in these dynamic Erdős-Rényi random graphs, we have a fixed initial graph. Okay, so this is potentially our fixed starting graph. Each edge is going to become active at rate lambda. Okay, so here's an edge that's currently inactive. And we're going to say that this edge becomes active at rate lambda. Edges are going to turn off at rate mu. So here's an edge that's currently active. We're going to suppose that this edge turns off at rate mu. So we have a Markov chain here, or a Markov process. We're again going to be interested in questions concerning the subgraph density. Okay, and in particular, triangle density. But now we're going to be interested in the triangle density at a specific time, t. So we can note that when the t is large, then this Erdős-Rényi random graph has forgot about its initial state. Okay, so it's forgot about its initial state. And each edge is in its stationary distribution. So each edge is on with this stationary probability. So in this case, it's very similar to just the standard Erdős-Rényi random graph. Okay. But we can, and then we can ask similar questions. Okay, so in this case, because in the stationary distribution, we have an Erdős-Rényi random graph, we also have a law of large numbers. So we can ask similar questions like, how unlikely is the event that there's an unusually large number of edges? Okay, so we can ask this question when t is very large, but we can also ask this question when t is much smaller. Okay, because we'll have a similar law of large numbers result in that case too. And again, we can ask what we can say about the structure of the graph given there's an unusually large number of triangles. Okay, so those are the same two questions as in the standard Erdős-Rényi, the static Erdős-Rényi random graph case. But we can also ask questions, new questions now, in particular about the path of the process given this event occurs. So we might know that the graph takes has a specific structure at time capital T, but then it has to take some kind of path to get to that value. So we can ask questions about that path using sample path large deviations. Okay, so our goal in this talk is to develop a large deviation principle that can be used to answer these questions. And we're going to come back to these three questions in the talk. All right, so the outline is we're first going to look at large deviations, but we're going to look at a simpler problem for large deviations. We're just going to consider the edge density. Okay, so we're not going to consider every subgraph density. We're going to start by just considering the edge density as a warm-up. Then we're going to move on to considering the full graph. And for that, we're going to need the space of graphons. Then we're going to derive a 2-point large deviation principle where we can answer which we can use to answer the first two questions that we saw on the previous slide. And then derive a full sample path large deviation principle, which we can use to answer the last question that we saw on the previous slide. Okay, so let's get into it. Large deviations for the edge density process. Okay, so there's n vertices, so there's n choose 2 potential edges. Okay, but for notational reasons, we're just going to let the number of edges be equal to k. Okay, so k is going to denote the number of edges. And to each edge in our Erdős-Rényi random graph, we're going to assign a process which we label x. Okay, so each edge has an associated process x. And that process is going to take the value 1 if that edge is on, and the value 0 if that edge is off. Okay, so these are just 0, 1 processes. If it's equal to 0, then it transitions to state 1 at rate lambda. And if the edge is on, so the corresponding process is equal to 1, then it transitions to state 0 at rate mu. It's going to be important, this probability here is going to be the important, this probability here. So the probability, so if we just focus on this one to begin with, this is the probability that the edge is on at time t, given that it was off initially. Okay, so that's what this means. And similarly, this probability here, which again is going to be important, is the probability that an edge is on at time t, given that it was on initially. Okay, so we can get specific or explicit expressions for these guys, which are going to be important. And we're going to be interested, at least for the next few slides, in the edge density. Okay, so this is the total number of edges that are on or active, and we're getting the sample mean. So we're dividing by the total number of edges. Okay, so this is a value between 0 and 1. We're going to need some kind of initial conditions. And we're specifically going to assume that the initial edge density converges to some constant value u. Okay, so we're going to say that asymptotically, the proportion of edges that are initially on is equal to u. And we can show that we can derive a law of large numbers. Okay, we can show that as the number of edges goes to infinity, so the number of edges here goes to infinity, then the edge density at time t converges in probability to this value here, which corresponds to its expected value. Okay, but we're interested in large deviations. Okay, so we're interested in questions like, how unlikely is it that the edge density at time t is greater than or equal to x when x is some unusually large value for the edge density? Okay. So the first thing we can do if we want to explore this probability that the edge density is unusually large is to try to derive an upper bound for the probability. And the first thing we can try to do is use Markov's inequality. But in this case, Markov's inequality is not going to suit our purposes. Okay, so we already know that this satisfies the law of large numbers. And this is not using the fact that the variance is converting to 0 at all. Okay, so this is going to be, Markov's inequality is going to be much too weak for our purposes. Okay. But we can try to use Markov's inequality in a different way. So we can just use the fact that the function e to the sx, when s is strictly bigger than 0, is a monotone function. And then note that this probability here is exactly the same as the previous probability, okay, using the monotonicity of that function. So the left-hand side of the equation is exactly the same, but the right-hand side is now different, okay? And because s is a free parameter, we can just take the infimum over all s that's strictly bigger than 0. And then we get what's called a Chernoff bound, okay? So now we have a much tighter upper bound on this probability that we're interested in. And the other nice thing is that this is a moment generating function. And this LKT can be expressed as the sum of independent random variables. So this is exactly what's happening down to this next step. Okay, we're just using the fact that this L is the sum of independent random variables. And then the moment generating function of sums of independent random variables can be expressed as a product. Okay, so that's all we're using to get down to here. The next thing we need to notice is that this probability, we know that it's going to converge to 0, but we want to get some kind of limiting result as the number of edges goes to infinity. Okay, so we need to arrange this expression a bit to get some kind of limiting result. Okay. So that's what we do here. We rearrange this expression to get the result. Okay, so we show that this limit is less than or equal to some function, which is going to be quite important, called the rate function, which has this expression here. Okay, and this expression is expressed as an infimum, but it can be written down explicitly, but the expression is quite ugly. Okay. So that's the upper bound on the probability. So we now need a lower bound, okay, to properly answer this question of how unlikely is the event that the edge density is unusually large. Okay, and it turns out that the lower bound is actually exactly the same. Okay, so we get the exact same lower bound as we did before. Okay, so what that means is that this probability that we're interested in, which is the probability that the edge density is unusually large, is equal to, or decays exponentially in the number of the edges, where we multiply k by the value of the rate function. Okay, so we've kind of answered our question of how unlikely is the event that the edge density is unusually large. Okay. So this can be re-expressed in a large deviation principle. Okay, and I've called this the 2-point large deviation principle for the edge density because we're only considering 2 slices in time. So time 0 and time capital T. Okay, and the other thing is that previously we only looked at the the edge density being unusually large, but we can also look at the probability that the edge density is in any set, either closed or open. Okay, so that's really all that this large deviation principle is saying. Okay, so we've got our large deviation principle, and now we'd like to answer some questions, and I'm just going to start by asking the exact same question as we saw before, just to give the structure of how you would use a large deviation principle. So in particular, if we're interested in this probability, the large deviation principle gives us this limiting value. And then we need to solve what's called, so we're interested in this guy here, and to get this decay rate, this exponential decay rate of this probability, we need to actually get a specific value for this, which we get by solving a variational problem. Okay, so we're minimizing this function over x equals 0.8 to get the infima. Okay. And this is a trivially simple variational problem because, as we can see here, so this is the rate function. This is a plot of the rate function. So because it's increasing on this interval, the minimum value is x equals 0.8. And we then know how quickly our probability decays. Okay. What about if we're just looking in some kind of small ball? Okay, so now instead of looking at the event that the edge density is unusually large or strictly greater than or equal to 0.8, how about we look at the probability that it's very close to 0.8? Okay, well then we have a slightly different variational problem, but the outcome is exactly the same. Okay, so we get the exact same expression for the rate that the probability decays. All right, what about, again, a slightly different event? Okay, now it's just, we're looking at the probability of the edge density at time capital T is greater than or equal to 0.8 plus epsilon. Okay, again, we have a similar looking variational problem, but now we get a different answer. So previously we got x equals 0.8. Now we get x equals 0.8 plus epsilon. And because our function is strictly increasing on the interval 0.8 to 1, this guy here is strictly bigger than the function when it was evaluated at 0.8. So the decay rate here is slightly larger. And we see that as k becomes large, this event is actually gets infinitely less likely than the event that, so this event that the edge density is greater than or equal to 0.8 plus epsilon becomes infinitely less likely than the event that the edge density is greater than or equal to just 0.8. Okay, so we can get a new answer, or we can use this observation to derive a general fact. Okay, so we can ask a question: what is the probability that the edge density is very, very close to 0.8, given that it's greater than or equal to 0.8? And we can use exactly what we just derived to show that this probability converges to 1. Okay, so that gives us a general rule. In particular, any large deviation is done in the least unlikely of all the unlikely ways. And in particular, our variational problem, it gives us the decay rate of this probability, but it also tells us how the large deviation occurs if it occurs. In particular, given the rare event occurs, the edge density in this case with arbitrarily high probability will be close to the solution of the variational problem. Okay, so that's in this example, but that's also in general. Okay, so basically, if you want to know the probability of a particular event and you use large deviations to solve that, you get how quickly that rare event, the probability decays, but you also get how it happens. So those two things are tied together by the large deviations. Okay, so that was just two slices in time. So we're just looking at time 0 and time capital T, but we can also ask questions about the process itself. And now we're going to get into sample path large deviations. So given that the edge density is unusually large, at time t, okay, and k is large, we can ask what path does this edge density process take, okay? And we can use a sample path large deviation principle to answer this question, okay? So a sample path large deviation principle can be derived in 2 steps. Step 1, we derive a finite dimensional large deviation principle. And in step 2, we establish exponential tightness. Okay, so we can see a parallel to convergence of stochastic processes. So for convergence of stochastic processes, we need convergence of finite dimensional distributions, and we also need exponential tightness. We also need tightness. And for sample path large deviations, we need finite dimensional large deviation principles and exponential tightness. So there's some parallels here. Okay, so let's start with step 1, deriving a finite dimensional large deviation process. Okay, so we're going to consider finitely many slices in time. So time 0, time t1 up to time tl, which is equal to our capital T. We're going to consider L points between 0 and 1. And we're going to take a small ball around each of these points. Okay. So using the Markov property, okay, and the total probability formula, the probability of being in every single one of these very small balls can be re-expressed in this way, okay, as a product. But if we can make these balls very small, okay, take these balls to be arbitrarily small, we can get something different for this, this part of the formula here, okay? So in particular, instead of just it being given that we're in a small ball around this value, we can just take it to be equal to this value, at which point we're just using our 2-point large deviation principle and the 2-point large deviation principle to get to this result. Okay, the 2-point large deviation principle and the Markov property. Okay, so we've just considered arbitrarily small balls here. And if we want a finite dimensional large deviation principle, we need to consider open and closed sets, all open and closed sets. Because our space is compact, we can cover any open or closed set with a finite number of very small balls, okay? So we can use what we saw on the previous slide to get our finite dimensional large deviation principle for the edge density. Okay, and this is all this says here, okay? We can then upgrade this to a sample path large deviation principle by taking our mesh here to be very infinitely fine, and then establishing exponential tightness. And the only thing to notice here is that our rate function is expressed in terms of an integral, but previously, or for the finite dimensional large deviation principle, this was a sum. Okay, so this sum has turned into an integral when we take our mesh very fine. All right. Okay, so now we have our sample path large deviation principle. We can answer the question that we saw before. Okay, so given that the edge density is unusually large at time capital T and K is large, what path does the process take to reach this unusually large value? Okay, so now we have a new variational problem. Okay, we want to minimize the rate that we saw in the previous slide, subject to the condition that the initial edge density is the correct one that we've specified, and that the edge density at time t is unusually large. But now we're minimizing over all possible paths. Okay, so this is a much more complicated variational problem. But it's one that we can solve, and we can write down an explicit expression that I don't want to get into now. But the point is that there's a unique minimizer, okay, and that the rate associated with that path is equal to the same rate that we had before. Okay, and what that means is that there's only one path that the process will take. So given that the edge density is 0.8 at time capital T, which is 5 in this case, there's only one path, or with high probability, there's only one path that the process can take. Okay, so this is illustrated on this graph here, where the y-axis, we have the edge density, the x-axis, we have time. Again, we're interested in time, unusually large edge density at time at t equal 5, and we've got this edge density be 0.8, which is here. The dotted path here is the expected edge density. And what the solid lines are the paths, the most likely path that the process takes to get to a particular edge density. Okay, so the one we're interested in here is 0.8. So with probability 1, when k is very large, the process will be arbitrarily close to this path. Okay, so we can say how unlikely this event is, and we can also say exactly what path the process takes to get to this unlikely value with an arbitrarily high probability. Okay. All right, so that finishes our warm-up. So now we're going to move on to looking at the full graph. All right, so previously we just looked at the edge density. Now we're going to take into account every single subgraph density at once. Okay, so this is the slide that we saw earlier. I just wanted to remind us what our notation is and what our goal is. So we're starting from a fixed graph. Edges turn on at rate lambda, edges turn off at rate mu. We're interested in subgraph densities, in particular the triangle density. So again, in this graph, the triangle, there's one triangle, but if the graph were complete, so if every edge was present, there would be 10 triangles. So the triangle density is 1 on 10. And we've got exactly the same stuff that we've got before. We're interested in the event. We're interested in the questions, how unlikely is the event there's an unusually large number of triangles? We want to know what we can say about the structure of the graph given this event occurs, and what path the process takes. Okay. So as soon as we try to do this, we're immediately hit with a problem. So to compare to the edge density case, for every number of edges, this random variable, which is the edge density, well, these random variables live on a common space. Okay, so they all take values between 0 and 1. And this space has a natural topology, which is the topology generated by the Euclidean matrix. In addition, the rate function can be expressed naturally as a function on this space. Okay, so that was fine when we were just looking at the edge density, but now our random variables are full graphs. Okay, so we need to find a suitable space for our graph valued random variables. And this space should satisfy 4 properties. Okay, so to establish our large deviation principle for our sequence of graphs now, our sequence of random graphs, we require a space such that, firstly, we want every random, so for every n, the random variables can live on this same space. Okay, so just like these guys all live on the space 0, 1, we want all of our random variables also to live on the same space. We want to be able to endow this space with a suitable topology. Okay, and we'll see what a suitable topology is in the coming slides. Okay, we also want this space to be compact, and that's because we would like to use small ball arguments. Okay, we'd like to we'd be able to take any closed or open set and cover it with small balls. Okay, so we want this space to be compact, and we also want the rate function to be expressed on this, easy to express on this space, and lead to variational problems that we can solve. Okay, so if we're putting a graph in here, infinitely large graph or arbitrarily large graph, that is going to lead to some very difficult variational problems. Okay, so we need a space that satisfies these 4 properties. And thankfully, recently, this space has been developed by Laszlo Lovács and a number of co-authors. Okay, and this space has been used in large deviations, which is exactly what I'm going to use it for, but also to solve a huge number of, well, quite a wide number of problems in graph theory. Okay, so this is a space of graphons. So firstly, what is a graphon? So a graphon is a function from the square to 0, 1, such that the function is symmetric. Any simple graph with n vertices can be represented as a graphon. Okay, in particular, the graphon is that represents graph G is equal to 1 if there is an edge between vertex nx and ny, and it's equal to 0 otherwise. Okay, so these particular graphons that represent graphs, they just take they can only take the value 0 and 1. And okay, so if we don't understand this particular formula, it may be helpful to just look at an example. All right, so here's our graph. We've got vertices 1, 2, 3, 4, 5. Here's the corresponding adjacency matrix. Okay, so vertices 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We can see there's an edge between 1 and 3. Okay, so that corresponds to this 1 here. Okay, and we can see that there's another one here because there's also an edge between 1 and 3 because the graph's not directed. Okay, so the ones here correspond to edges, and this adjacency matrix is symmetric. All right, so that's the adjacency matrix. Here's the corresponding graphon, and you can see that all we've done is divided this guy up into little squares and then drawn colored in black all of the squares that correspond to 1. Okay, that's what we've done to get this guy. And these black squares correspond to squares where the graphon is equal to 1. Okay. All right, so that's the graphon representation of a graph. So step 1 is done. We can describe any graph with n vertices as a graphon. So we can embed all of our random graphs on the same space. But we need this space to have some nice properties. So we're interested in the subgraph densities. Okay, so we have, for any simple graph H with k vertices, so H might be a triangle and k would then be equal to 3. We can express the subgraph density, or we can get the subgraph density using this formula. Okay, so it's not particularly important what this formula is right now, but the important thing is that we can recover the subgraph density or the triangle density we're often going to consider using this formula from the specific graphon. Okay, so again, in this example, one triangle where if it was a complete graph, there would be 10. So the triangle density is 1 on 10, and we can recover this using the formula. Okay, so now we need this space to have a suitable topology. And to do this, we're going to endow the space with something called the cut distance. Here's the definition of the cut distance between two graphons, H1 and H2. This particular formula for the cut distance is not so important for this talk, but what is important is that the subgraph densities are continuous with respect to the cut distance. And this space is appropriate for establishing limits for dense random graphs. All right, so this is important because we want to know if we have a sequence of graphs whose graphons converge or whose cut distance goes to 0, because we're interested in questions about the subgraph densities, we need this to be, we want to know that the subgraph densities are going to converge as well. Okay, so we get this, this fact that the subgraph density is continuous with respect to the cut distance tells us that. Okay, so that's very important. So this wouldn't be the case, for instance, if we considered the weak topology. So we wouldn't have this. Okay? And then we couldn't answer any of the questions that we're interested in about subgraph densities. And the next thing is we want to get limiting results. So if, and we can with this cut distance, but we wouldn't be able to, for example, if we took the L1 distance, then an Erdős-Rényi random graph, as we take the number of vertices large, wouldn't converge to anything. So this would be, this would also be the wrong space because we wouldn't be able to prove any convergence results either. Okay, so this, this cut distance gives us the right topology to prove our convergence results on. Okay, so to try to kind of give you a sense of this last point, we're going to look at some limits. Okay, so let's first consider a sequence of Erdős-Rényi random graphs with edge probability 0.5. Okay, so here's what the graphon looks like, or an outcome when there's 10 vertices. Okay, 20, so again, the edge probability is 0.5, 50, and 100. And what we can see is that if we kind of blur our eyes a little bit, this kind of looks like a gray graphon. Okay, this approximately looks gray if we kind of take off our glasses and look at this. Okay, so it turns out that in this space, this converges to a constant graphon, okay, which is just equal to 0.5 everywhere. Okay, so what this means, because the subgraph densities are continuous with respect to the cut distance, to get the edge density, we can just replace the particular graphon with our smooth graphon here, okay, and then use our nice formula to calculate the edge density. And we can do the same with the triangle density. Okay, so the triangle density, as n becomes large of our graph, converges to the triangle density in our nice smooth graphon, where we can use our nice formula. Okay, so in this case, we know that the triangle density is 0.125. Okay, for our Erdős-Rényi random graphs. Okay. All right, let's look at another example. So let's now say that edges, there's two types of vertices. Vertices whose label is less than n on 5, and vertices whose label is strictly bigger than n on 5. Okay, so the vertices whose label are less than n on 5 live here, and then bigger than n on 5 live here. Okay, and the edge probability between two vertices whose label is less than n on 5 is 0.288. So that corresponds to this square here. The edge probability between one vertex whose label is bigger than n on 5 and one vertex whose label is less than or equal to n on 5 is 0.7125, and that corresponds to these two rectangles in our graphon. And finally, the edge probability between two vertices whose label is strictly bigger than n on 5 is 0.4, and that corresponds to this kind of square here. Okay. And if we take n to be bigger, so now we have the number of vertices being 20, 50, and 100. And if we kind of blur our vision a little bit, we can see we get convergence to a smooth graphon again. Okay, so here's our smooth graphon. Okay, with the values corresponding to the probabilities. So again, due to the fact that the subgraph densities are continuous with respect to the cut distance, we get convergence of our edge densities to the density in our smooth graphon. Okay, so the edge density is 0.495 here, and the same with the triangle density. Okay, so the triangle density is 0.125. Okay, so there's also one more thing in these two examples that I wanted to explain. The triangle density in the two limits that we've seen is exactly the same. Okay, 0.125. So that explains why I chose these values. But the edge density in this example is smaller. Okay, because the edge density in the Erdős-Rényi random graph case was 0.5. Here, the edge density is smaller. So this shows that you can generate more triangles occasionally if you kind of choose carefully where to place your additional edges. Okay, so this has fewer edges and the same number of triangles. All right. Okay, we're going to consider one last example, but now, and the example is going to be exactly the same as the example we saw previously. We're just going to mix up the vertex labels. Okay, so again, there's going to be two types of vertices, but instead of the labels of the type 1 vertices being strictly less than or equal to n on 5, it's now just going to be every vertex whose label is divisible by 5. Okay, so we're just kind of mixing up the labels. The graph itself is the same if you don't care about the labels. Okay, so this is what we get with n in 20, 50, and 100. And what we see if we kind of blur our vision is we get something that's close to a constant graphon again. Okay, but we don't get convergence because we know that this shouldn't converge to a constant graphon. Okay, because the subgraph densities don't converge to the densities of a constant graphon. Okay, so if we did equip this space with the weak topology, then we would get convergence to a constant graphon, but we wouldn't get the corresponding convergence of the subgraph densities. Okay, so this is why we shouldn't use the weak topology in this case. But this also makes a larger point. So in particular, this sequence of graphs that we saw, it doesn't converge to anything with probability 1 in this space, but also it doesn't have, with probability 1, it does not have a convergent subsequence either. Okay, so this means that this space here is not compact. And remember that to prove our large deviation results, we wanted to work on a compact space. Okay, so we need to kind of modify our space a little bit. And we're going to do that by kind of removing the issue that we saw on the previous slide with the mixing up of the vertex labelings. Okay, so we're going to consider the set of measure preserving bijections. Okay, and this set you can just think of as relabelings of the vertices. Okay, so this is just going to be some relabeling of the vertices. We're going to say that two graphons are equivalent if you can relabel the vertices and then their value is the same. And we can form a space by taking the quotient with respect to this equivalence. Okay, so we basically just any graph that that is the same up to relabeling, we just glue those graphs together. We can endow this space with a metric where we use the cut distance. And we can note that, well, it's known that the topology of this space, or sorry, we have convergence in this new space, if and only if all of the subgraph densities converge for every simple graph H. Okay, so basically the topology generated by this cut metric is the same as the topology generated by the subgraph densities. And importantly, this space is compact. Okay, so we now have a compact space. The final thing we need is to be able to express our rate function on this space. Okay, so for that, we first need an assumption, and we're going to assume that our initial graphs, so our initial graphons converge to some value u in this space of graphons. Okay, as n goes to infinity. Okay, so if we extend the domain of the rate function that we saw earlier to w squared, okay, so earlier we were putting values between 0 and 1 in here. Now we're going to put graphons in here. Okay, by letting this guy, where we're putting graphons in here, be equal to the integral over the square of the rate function that we saw earlier that was connected to the edge density. Okay, so here, these are values between 0 and 1. Okay, so this is a candidate rate function on our space. Okay, on our space of graphons. And basically all this says is that the local edge density has to match for every x and y. So it doesn't matter if you don't understand that, but this is really about matching local edge densities. Okay, so this rate function is a function on W, but we want to work on this space because it's compact. Okay, so we need to slightly change the definition of our rate function, and we do that by again using our relabelings, so our measure preserving bijections. Okay, so here's basically the main result that that Frank, Michelle, and I came up with, which is a 2-point large deviation principle. Okay, so 2-point because we're looking at 2 slices in time 0 and time t. And what we've basically shown is that this rate function that we've kind of guessed is the correct one. Okay. So here's the large deviation principle, but what's perhaps more interesting is what we're going to use it for. And we're going to try to use it to answer the questions that we saw at the beginning of the talk. So we're going to assume that the initial graphon, okay, is a constant graphon that's equal to lambda divided by lambda plus mu. And this just says that we're going to assume that we're starting from the stationary distribution of our process, a typical outcome of the stationary distribution of our process. And we're going to say R is a value that's greater than or equal to this, this edge probability. So this is the stationary edge probability in our dynamic Erdős-Rényi random graph, and R is a value greater than or equal to. Which means that the question, how unlikely is this event? Okay, is how unlikely is the event that the edge density is unusually large, okay? And what can we say about the structure of the graph given it occurs? So again, we've seen that we can answer both of these questions if we can solve a variational problem. Okay, so here's the corresponding variational problem that we need to solve. We need to minimize the rate subject to the condition that there's enough triangles in the graph over the space of all graphons. Okay. So due to time, I'm not going to go through this next slide, but I'm going to say that we can actually solve this variational problem. Okay. So that's what we have here. Okay. So basically we're asking, in the end, we're asking the question, when, so we've got it, sorry, I'll go back. So this variational problem, we need to optimize over all graphons, okay? But there's a natural solution here, which is just putting the graphon, the constant graphon R in here, okay? So the Erdős-Rényi random graph outcome as the minimizer, which will have R cubed triangles, all right? So we're going to ask a simpler question because it's too complicated to get the exact minimizer in every situation, but we might be able to get know when the constant graphon is the minimizer. Okay, so a simpler question is, when is the constant graphon the unique minimizer of this variation problem? So that's equivalent to asking, are the extra triangles more likely to be formed by adding a large number of edges sprinkled uniformly? So that corresponds to the symmetric regime, or fewer edges added in some kind of special structure. That corresponds to the symmetry breaking regime. Okay, and we can determine when we have these two cases. Okay, so that's what this theorem is saying, but it might just be easier to look at a picture. Okay, so here's the phase diagram for this problem. So here we have R, and remember R cubed is the unusual outcome of the triangle density, so the unusually large triangle density that we're interested in. T is the planning horizon, so time capital T. And shaded corresponds to symmetry breaking, which is when the optimizer is a non-constant graphon, so is not equal to the constant graphon R, and the unshaded region is a symmetric regime where the optimizer is the constant graphon R. Okay, so to understand this picture, it might be best to look at the two extremes. So 0 here, so time equals 0, and in this case we're starting from 1 on 9, okay, which is this value here. So what this basically says is that if the planning horizon is very small, then the most likely way that an unusually large number of triangles occur is if they're arranged in a special structure that doesn't look like an Erdős-Rényi random graph. Okay, so that's why this whole kind of region above 1.9 is the blue region. And that's because when the time is very small, or the time window is very small, a huge number of edges need to be added in a very short period of time. And that's very unlikely. So the least costly way that happens if they're added in some special structure. So if there's fewer edges added in a special structure. Okay, so that kind of helps us understand what this is saying. And the other thing we can do is look at taking the planning horizon to be very large. Okay, and in this case, we just get back to the Erdős-Rényi random graph case. Okay, because when time is large, the graph has forgotten about its initial value, and we just have an Erdős-Rényi random graph, a standard Erdős-Rényi random graph. And when Chatterjee and Variational first came up with this, first kind of looked at this problem, they were quite excited to see a double phase transition. So as we increase R, we go from symmetric to symmetry breaking and then back to symmetric, which is kind of quite a strange result that was conjectured for a long period of time, but they managed to prove it using their large deviation principle. And we see it again here for finite time t. But what we also see is some new behavior. So we see new phase transitions on a new double phase transition, which is something that I wasn't expecting at all. And in particular, we now have phase transitions in the planning horizon. So if we look at the value r equals 0.5, so 0.5 cubed is the triangle density we're interested in for a specific value of the parameters, then we see that we're originally in the symmetry breaking, then we go into symmetric, and then we go back to symmetry breaking. So we have new phase transitions that we don't understand at all. Okay. Well, I mean, that are a complete surprise to us. There's no intuitive reason why this should be the case. Okay. Okay, so that's one thing that the dynamics showed up that were quite surprising. There's one more thing that I'll just quickly get to before I finish that was again quite surprising. So now we've looked at the question, how unlikely is there to be an unusually large triangle density at time capital T? But we can also ask, what path do we take to that unusually large triangle density in the space of graphons now? Okay, and we can ask a more general question. Suppose the process starts near a graphon U and is conditioned to end near another graphon R at time t. What path is the process likely to take? Is there a unique most likely paths, or are there multiple most likely paths? When we looked at the edge density, we could give a specific most likely path, and it was unique. Okay, so to answer this question, we can use sample path large deviations. Okay, and here's finite dimensional large deviation principle, sample path large deviation principle. And to answer this final question, we end up with a variational problem that's similar to what we had earlier. Okay, so to answer the question, what path does the process take if it starts near a graphon U and ends near a different graphon R at time capital T? And is this path unique? We have to solve a variational problem. Again, that's the theme of this talk, where we minimize the rate function over now the space of graphon value trajectories. Okay, so this is quite a difficult variational problem. The initial graphon is U and the final graphon is R. Okay, so if what we found is that if U, so if this initial graphon is constant, then the variational problem has a unique solution that can be expressed explicitly. However, in general, this variational problem may have multiple distinct minimizers. Okay, so it may actually have multiple solutions. And that's quite a strange result because basically what you're doing here when you're specifying that the graph is close to a graphon is you're specifying every single subgraph density. Okay, and then you're looking at the paths that the graph takes between these two graphons. And when the path is not unique, it means there's two most likely ways, at least, to get to this, to get from your original graphon, where every subgraph's density is specified, to your final graphon, where every subgraph density is specified. So the subgraph densities can take two different paths to get there in an equally likely way, which is, to me, a bizarre result. Yeah, so I won't go into that too much because I think I've run out of time. I just like to just point out that we've looked at Erdős-Rényi random graphs, but in the future, we'd like to look at more general edge dynamics. And here's some references, and thank you for your time.
Okay, thank you very much. We can ask some quick questions. Are there questions and comments? Please unmute yourself if you have questions.
My quickly comment for part 1, if I correctly understood, L sub k of t was basically a binomial random variable with known success probability divided by k, right? The density.
Well, I mean, it's close to that, but of course there's they're not independent Bernoulli random. They're not IRD Bernoullis because the initial edge density is specified. So if the initial edge density was 0 or 1, then indeed that would be the case. But when the initial edge density is any value between 0 and 1, then it's not just the binomial random variable.
Yes, but still it's a sum of independent guys.
That's correct.
Right?
Yeah, yeah.
So, but they may have initial conditions lead to slightly different probabilities at the end.
Yeah.
Of having or not having edge.
Yeah, indeed.
Okay, so I suspect that it might be possible to get even a stronger result, to get not logarithmic probabilities, logarithms, but precise ones using standard techniques for this thing.
Yeah, so I agree with you. So this is not original work. This is more an introduction to the area to help to understand the Erdős-Rényi stuff. But I agree with you. That is definitely possible.
So can I ask?
Yeah, please.
In the example you gave, where you start in some sort of fairly uniform way and go rapidly to having a lot of triangles very quickly, and you have symmetry breaking, it's the sort of thing you get. You get a complete subgraph, for instance, so you have lots and lots of triangles with relatively few edges. Is that the sort of picture you get, and then otherwise empty, or what?
I can show you basically what you get. You get something that looks like this here, which I kind of took from the proof.
Okay.
It's not so obvious why you get this, but yeah, I believe that you get something like this.
Okay.
Where there's kind of a I think it's because if some intuition is because I think if you get one vertex here and two vertexes here, then two of the edges are corresponding to this larger probability, and that gives you more triangles. Two of the edges in the triangle.
So putting in, as it were, a large complete subgraph would be too difficult for other reasons.
I think that's right, but I'm not sure that this problem's been solved. But what I did is I went to the proof where they look at the most efficient way to add triangles without adding too many edges, and this is what they came up with. But you might be correct that like a large complete graph is the way to go, but I'm not sure.
Yeah, I was going to ask, just in general, kind of how are you solving these variational problems? Where does this picture come from? And that can be quite hard, right?
Yeah, so it's interesting. So if we go to this is the variational problem that causes all the trouble. So Chatterjee and Variational, so to solve, we couldn't solve this variational problem. What we could do is answer when is it optimal to put in the constant graph on R. Okay, that's as well as we can do. We can't tell you what the graph looks like when you're in the symmetry breaking regime. But even that took a lot of trouble to get to that point. So Chatterjee and Variational kind of posed this, had this same variational problem, but they couldn't solve even this simpler problem. I mean, they came up with a nice way of approaching it, but it took, it wasn't until Lebetsky and Zhao a few years later came up with a new method to even kind of solve this simpler question that you could even get like these phase transitions graphs. So it's a difficult problem. Mm-hmm. A rambling way of saying what I'm trying to say.
Yeah. Well, that's what I recalled that paper as well. So But I thought that was the thing that maybe Andrew was saying, that they found too, that, you know, they had some setting where they had two regimes, where one, you get a lot of triangles by just having big clique, and then sometimes you get the triangles by looking like a Erdős-Rényi graph with the wrong parameter, basically, something like that. So,
yeah. So I went.
I don't remember the detail.
Yeah. I mean, I went through the proof of that paper to come up with this thing, where I was trying to create an example with a large number of triangles without additional edges, and this was it looked at some version of this was what's in the proof of their paper for the symmetry.
Okay.
So yeah, so I mean, I agree with you that logically you want to add a big click, but that's not what I saw in the proof of their paper.
Yeah, I mean, there's some constraint coming from the edge densities too, so that's you're fighting between those things in some sense.
Yeah.
Okay, other questions?
Well, one more would be, what sort of graphs are you going to look at that are more general than the Bernoulli graph? You're going to look at sort of...
Yeah, so that's a good question. So we're just finishing a paper now where we're trying to introduce dependence between the edges. And one way you can do that is giving each vertex a type, and then the vertex type will fluctuate and will affect the probability that edges are connected to that vertex. Okay, so that's one way of doing it. We're almost finished kind of that way. And the next kind of class of problems that we're looking at would be a class of dynamics, is things that are kind of pop up in more applied situations. So things like epidemics on dynamic random graphs would be something that I'd be interested in looking at. It might be too ambitious to get a sample path large deviation principle in that case, but maybe like a functional law of large numbers, or things like voter models on dynamic random graphs, where you sever edges between people you're not friends with or hold a different opinion with. So these are the things that we're thinking about in terms of the more general edge dynamics.
Right.
Okay, time is up, so probably it's better to stop it here. Let's thank Peter for the interesting talk. Thank you, Peter. All right, I'll see you guys in the next talk.